はい、じゃあちょっと too much content, so therefore I will explain the briefly first. ちょっとじゃあね、ちょっとこれを見ると、例えばですね、ここら辺のことがこの辺のことがまあファンダメンタルですね。なんかこうやってでなんかシングルセルの話がこの辺にあって、シングルセルの話があって、まあシングルセル。これはセルメンブレンの話があって、でそれhuman cells and from here the cell operation, mechanical operation or some optical operation and so on, how to operate, how to manipulate one cell っていう話があって、でなんかマイクロマニピュレーターとか、あるいはsome injection とか、and then from here the what is the cells dynamics、まあ、cells dynamic characteristics の話があって、how to measure its single cells dynamics っていういろいろメソッド、cellular method is explained here、これとかこれとかこれとか、まあ explained here, and then some experimental result shown here, 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 and here. And then the final part is about the birth and death about the cell. Okay? です。だからこれが third part。これが from here is the third part。この辺が second part。second part はだいたいこの辺からが second part。ここから上が first part ね。じゃあ、まあ、ここちょっとスキップして、じゃあ、ここからいきましょうかね。はい。じゃあ、シングルセルの話ね。シングルセル。まあ、いろんな、これさっきのゾウリムシっていうのは、これ、パラメシウム。これ。This kind of some kind of なんか、here is here, and then it can move. とか、of course, human cell is also the single cell。シングルセルで、あとエスチェリシアスコイル、まあエクセリシアコイル、大腸菌っていうのもシングルセルで、what is the largest cell in the world? そう、some of the egg, one's egg is the largest one ね。エッグセルで、エッグ、ちょっとよくわかんないんだけど、また名前忘れちゃったので絵を描くんだけど、なんかさ、こういうのいるでしょ、こういうのなんか、はい、こういうののエッグセル、エッグ、これ例えばオーストラリアとかオーストラリアとかに住んでるバーランニングバードのなんかこのエッグのはだいたい more than 30 cm and inside of this is one single cell. And so therefore that is the largest cell maybe in the world. でそれから longest cell. What is the longest cell? Yes, yes. Some nerve cell is the long. For example, some human cell, the human nerve systems. So, for example, in the leg, some nerve cell is more than 30 centimeter, of course. Also, so therefore, that some of the nerve cell is the longest. じゃあさ、まあこれチキンのセルっていうのはまあ大体エッグヨークはまあシングルセルだけど、まあチキンは例えばこれ例えば6センチ、6センチメーターとか4センチメーターだけど、この This bird cell is the most largest ね。で例えばカエル、フラッグのこういう、エッグはこの中にこうエッグがこう入ってるんだけど、これはエッグそれぞれがセルだよね。 ブラックの。っていうのがここに書いてあって、このジェラチノウスリボンの中にはこのシングルセル is here。シングルセル、シングルセル。この 3番目に書いてあるのは何ですかって言ったら、マンダリンオレンジとかいうの。例えばこういうオレンジ、こうなってますね。オレンジのこの一つ一つなんかなんだっけ、ニュクレウスじゃなくて、ワンシングルモジュールパーティクルってあるよね、なんかスモールパーティクル。こう袋に入ってこうなってるよね、なんか粒が。でこれはセルですか？これシングルセル？これシングルセル？これはノット。これはシングルセルの中、これはシングルセルじゃなくて、これの中にseveral cell is there inside of this. So therefore, this one particle is not the single cell. このそれぞれがこれで、この inside of this, the several cell is contained. グレイン。で、パラメシウムとか、ボルタイスとか、ベルアニマとか、まあそういうセルは、まあセルですねということです。で、セルとは何ですか？セルとは何ですかっていうのは、the minimum unit. It is inside of this nucleus. Nucleus is a center of the cell, and some neighboring cell body and plasma membrane. Plasma membrane is the separated inside and outside of the cell. でとにかくセルというのは何かまあ多くはヌクレウスがあって、なんかメンブレンで separate inside plasma body and the outside is separated. Some of the cell, prokaryotic cell は not clear cell, not clear abundantly the nucleus, but some of the part material is the condensed. So this is like this. And some nucleus is here, so the double membrane is separate from other part of the cell. So therefore the some ちょっと覚えてないんだけど、なんかこういうダブルレイヤーシステム、ダブルメンブレンシステム is the separate the inside and outside of the cell. nucleus. で、most of the animals, creatures is this nucleus has. ちょっとなんかビデオをピッと見ると、どっか例えばこれか。
Franke, medeoprichter van Kleef Franke. Wij zijn een grafisch ontwerpbureau dat zich richt op interactieve oplossingen voor informatie- en datavisualisatie. Vanuit dat specialisme ontwikkelen wij oplossingen voor complexe onderwerpen. We gaan kijken hoe we daar een goede communicatieve oplossing voor kunnen vinden. De lichting zelf begon eigenlijk als een eigen geïnitieerd project, waarbij eigenlijk wij iets proberen te doen met onze fascinatie voor de celbiologie en het verdere genetische onderzoek. waar veel van onze opdrachtgevers die we in de afgelopen jaren hebben gehad onderzoek naar deden. Vandaar kwam we eigenlijk met het idee van hoe mooi zou het nu eens zijn dat mensen zelf als het ware in een cel kunnen stappen en daarmee kunnen interacteren. En zo kunnen zien wat er gebeurt met de eiwitten en wat er gebeurt als de cel reageert op verschillende stoffen. Om zo eigenlijk iets, ogenschijnlijk is altijd heel ingewikkelds en heel super klein, waarvan we allemaal weten dat het in ons lichaam plaatsvindt, eigenlijk eens een keer tastbaar proberen te maken.
De bezoeker is voor de cel eigenlijk een soort van dirigent. In die zin, je kunt de cel in een bepaald scenario brengen. Je kunt stoffen toevoegen, de cel kan kapot, de cel kan weer gerepareerd worden. Dat kan de gebruiker doen door simpelweg aan de rand van de cel te duwen tegen die echt een extra onderdeel van een onbegotte tentoonstellingsruimte. Die zal bestaan uit ingrijpen in biologische processen. Ze kunnen UV-straling aanzetten of ze kunnen suiker toedienen aan die cel. Andere chemische stofjes toedienen aan de cel en onmiddellijk zien, visualiseren wat daar gebeurt.
One self-expression about using the projection system. ね、なんか some museum とか some fair it is exhibited. はい、で、例えばシングルモノセルラーオーガニズムでムービングセルはパラメシウムとかアミートとかいうのは it can move by itself. で、パラメシウムっていうのはこのセリアっていうスモールヘア by using this it can move. アメーバは deform its shape and then it can move. パラメシウムはどんなやつだったですかって言ったら maybe you knows.
This is a paramecium at lunchtime. I'm using a Nikon 40X plant achromat lens on a Nikon fluopod scope with a Nikon fluopod phase condenser.
Like なんかランチタイムとか言ってますね。アメーバどうだったですかって言ったら、ちょっと待ってね、アメーバはchange its form arbitrarily like this. A fluiding in the inside of the plasma is moved, so therefore it can move like this. ですね。ということで、これをしまって、で次のページはゾウリムシですね。ユーベナこういう弁毛っていうのはフラゲルっていうのがあって by using it can move here or there or it can move in the side で by using this kind of the and thenこのモーターmolecular motor. Many people wants to declare what is the mechanism of these molecular motors. How to move this fragment. それはどんな感じですかといったらこんな感じですね。これを使ってこう動いてきますよ。ここに動いてますね。でした。でそれでマルチセラーオーガニズムのミニマムユニットはこのセルですよ。セルね。こっちの場合は、アニマルセル。こっちの場合はプラントセル。プラントセルのThe difference is, main difference is maybe you have learned the rigid wall membrane, and also the chloroplast, green element is inside of the plant cell が、まあ、メインディフェレンスということで、これとこれですね。Introduction to cell、 ちょっとこれ見てみますか。
The time we participated in an earthworm dissection, the time we took apart an album thing ever, the animal cells, billions of animal cells, that's fascinating. In fact, it really makes you reflect on some of the incredible statements of the modern cell theory. The modern cell theory includes the following. First, that the cell is the smallest living unit in all organisms. And second, that all living things are made of cells, one or more cells. The amoeba I observed was a single-celled organism, so unicellular. Humans are made of many cells, so multi-cellular. And third, all cells come from other pre-existing cells. You know, cells have their own little world inside them. They carry genetic information, they can divide, many have functions and processes that their organelles, structures inside them, can take care of.
というわけで、まあいいや。ということで、コンポーネントオブセルっていうのは、まあいろんなものがありますね。ニュクレウスっていうのは、まあセンターですよ。ニュクレウス。であって、エンドプラズマとか、ゴルジーボディとか、リソソームとかであって、ミトコンドリア。ミトコンドリア is a very interesting part because it is said the mitochondria is a different creature. It is this theory is proposed. Another living creature is symbiotically living inside of the cell. っていうのをなんかリン・バルグリューズ is said proposed 1970。これは例えばここどっかにここに書いてあったやつにするんだけど、ちょっと待ってと覚えてないんですけど、ちょっと待ってこれやめとこう。これは ATP 加算分化の話か。これはセルストラクチャーのファンクション、セルセルアンディッツ、セルセルス。ちょっとこのラップだけ見ましょうか。
Today's the day we're gonna learn about the cell. If I teach it okay, you'll know it very well. So listen up, sixth graders, no room left for haters. Let's talk about the building blocks of life, cells that make us. Cells, they're made of organelles. Try to pull it fast when the cytoplasm gels. The nucleus takes over, controlling everything. The party don't stop till the membrane box is seen. Inside the vacuole, we can float around for hours. Running around with chloroplasts, loving some like chakras. Cells, they're made of organelles. First things first, there's two different types. Animal and plant cells that make up all life. The little things that make up microscopic cells, the main structures there, we call them organelles. Now let's break it down and get some information. How do cells work? It's a crazy combination. Cells, they're made of organelles. Try to pull it fast when the cytoplasm gels. The nucleus takes over, controlling everything. The party don't stop till the membrane box is seen. Inside the vacuole, we can float around for hours. Running around with chloroplasts, loving some like chakras. Cells, they're made of organelles.
The cell membrane is the border patrol. Who can cross over? The membrane lets them know. The gooey stuff inside is called the cytoplasm. It holds the organelles. Don't worry, present as in the middle of the cell you find the big brain. The nucleus surrounded by nuclear membrane. Don't forget the vacuole is filled up with water. It's basically provided from the
Vacuum's getting hot. Cells, they're made of organelles. Try to pull it fast when the cytoplasm gels. The nucleus takes over, controlling everything. The party don't stop till the membrane box is seen. Inside the vacuole, we can float around for hours. Running around with chloroplasts, loving some like chakras. Cells, they're made of organelles.
The mitochondria is something every cell needs, breaking down the food and releasing energy. There's a place inside the cell where chemicals are stored. The squiggly goopy body is releasing even more.
You'll hang in the cell is endoplasmic reticulum, synthesizing enzymes for respiration. And none of you still think that this rap is whack? Remember ribosomes making proteins getting jacked. Cells, they're made of organelles. Try to pull it fast when the cytoplasm gels. The nucleus takes
というわけでこれサマリーですね。OK です。でだからセルメンブレンっていうのはこの、プラズマメンブレンでフルイドモザイクモデルっていうのがあって both facing both sides and this the hydrophilicity part is the outside and the hydrophilicity part is the inside and then some part is opened and closed. This is using some metabolic material is there, and this is some gate of some material is go through the outside to the inside and to the host through the outside. So therefore this is called sodium pump, natrium pump. And the inside of the cell is cytoplasm. It means some kind of material is halfly liquid, halfly solid. So therefore it is called solid form, and not liquid form. And many proteins and some the large scale molecule is there inside of the cytoplasm. これもセルメンブレンのやつっていうのはフルイドモザイクモデル。例えばこいつを見ると
Between the living machinery of the inner cell and the harsh conditions of the outside world stands the cell's plasma membrane. As crucial as this barrier is, it's surprisingly flexible. Push it and watch it move. Poke hard enough and it might break and begin to regroup. The lipid molecules of the membrane naturally assemble in a double layer because their tails repel water as their heads attract it. Throw in some cholesterol and a few carbohydrates, and you have the basic structure of a plasma membrane. Within these lipid molecules, we also find different proteins which do various things for the cell. For instance, they receive signals from the world outside, or they transport nutrients and waste. So nature composes the membrane with a combination or mosaic of different lipids, carbohydrates, and proteins. And these molecules are not stationary. They constantly move within the structure, fluidly changing their positions. The survival of all life rests on this veil of material. A supple membrane, just 2 molecules thick.
というような感じで、なんだっけ、プロテインのゲートシステム is there for the plasma membrane, 2 layers model. というわけで、human cell, the very different kinds of more than 200 kinds of cell is composing the human being, the body, and the number of cell of human being is more than 6 trillion number, and very different kind of cell is there. You see the last week the hair cell in the inside of the ear, and also the sperm and the egg cell, and also the nuclear and nerve cell and the muscle cell, and so on. There are many kinds of cell is there. でここからがセルダイナミクスの話で How to manipulate the cell, single cell. The mechanical way is, for example, the suction, absorption, and the contact needle insertion or insertion and pipetting or cutting, drilling, and something injection method is also there, so using the micro-pipette and ultrasonic waves or something. And electrical manipulation is potential measurement, current measurement, electrical stimulus, and the electric injection and heating. The optical way is optical teaser, like the laser trap method. Optical tweezers method is also there. And so therefore the ultraviolet ray or laser light, some part is needled, some part is the breakout, and so on. And the chemical way is looks like the cross link between the DNA or the pulsemid and so on. Some molecule is separated or destroyed or something. And also some ion injection method is also there. So therefore the pH consistency can be adjusted or something. ちょっと例えばオプティカルトゥイーザーメソッドですhere。これは this cell is deformed by projecting laser beams. And it can be moved somewhere, some directions, and so on. Some operations is there by using the optical beams. Changing direction. これについてはここに Interaction of Vehicle Tracking っていうのがあるので、ちょっとそれを見ましょうか。
Welcome to the Bioinstrumentation Teaching Lab at the MIT Department of Biological Engineering. I'm Steve Wasserman.
And I'm Stephen Nagel.
I assume you've tuned into this video because you would like to make quantitative measurements with laser tweezers. If you were looking for cute kid videos, you've made a horrible mistake.
Optical tweezers can apply measurable forces to micron-scale dielectric particles. This capability offers a unique and valuable tool to manipulate cells and cell components, as well as measure mechanical properties at the micron scale. For example, instruments just like this one have been used extensively to investigate the mechanical properties of biological polymers, as well as the force generation mechanisms of molecular motors. In many cases, the force is actually applied to a microsphere which is attached to the molecule of interest, as a way of providing a convenient handle.
To make quantitative measurements, the instrument records the displacement of a trapped particle over time. The exerted force is very nearly proportional to the displacement, so the trap can be modeled as a linear spring. Accurate force and position measurements depend on careful calibration of the position detector responsivity R and the trap stiffness alpha, also called the spring constant.
The properties of the trap are a function of the laser power, the bead diameter, bead composition, as well as the optical properties of the surrounding medium. In this video, we will show you 3 different methods to calibrate the trap.
Let's start with a review of the single beam gradient force laser trap. In this system, a high numerical aperture lens brings the laser beam to a sharp focus. Light rays entering a microsphere at the center of the trap are refracted. An example ray is shown at the extreme right of the beam. Refraction changes the momentum of the photons of the beam, as indicated by the green arrow. The particle undergoes an equal but opposite change in momentum. The ray refracts again as it exits the particle, which adds to the force on the microsphere. Some of the photons reflect off of the microsphere. These generate a momentum change in the opposite direction. The overall force of the particle can be approximated by adding up the contributions of many rays. For a particle in the center of the trap, all of the forces sum to 0. If the microsphere moves out of the center of the trap, the refracted light also changes direction. The forces are no longer in balance. There is a net force on the particle toward the middle of the trap, so the force exerted by the light tends to restore a particle to the center of the trap. The strength of this kind of optical trap depends greatly on the gradient of the light intensity, so it is important to use a well-aligned instrument to achieve best results. The optical trap used in this demonstration was developed here in the instrumentation lab. If you are considering making a trap of your own, Thor Labs offers a kit that includes all of the bits needed. Search for part number OTKB on the Thor Labs website.
まあいいや、ということで、というようなオプティカルトゥイザー is there. Okay? Laser trap method ね。 And also the chemical manipulation method is also there. Some chemical stimuli or vital staining or making color for the observation. Yes, so I will introduce some examples. Actually, some mechanical injection method by some needle is practically used. This is a mechanical sticks. This is the operation handle. And this handle operation is by using some gear system, and then the bit ratio micro motion is generated by using this mechanisms. So the gear ratio or movement ratio can be changed. For example, in this case, the 450 to the 30. This XYZ stage motion is also there, and also some handles can rotate. One rotation moves for example, 18 millimeter, but the other small part rotation makes the 200 micrometer per round. Or not only the mechanical method, but also some the fluid liquid method or something is also there. This is operation parts, three-dimensional joystick or handle is there, and the air tube is connected to this stage at needle operation stage, and by using it, it can be moved more slightly. For example, the minimum movement is 2.5 micrometer at the end of the needle. The similar product presently looks like this.
Feature 1. Revolutionary one-step pipette positioning. The pipette retracts simply by pulling the lever upward. With one push of a button, the pipette returns to its exact position before it was retracted. Feature 2. Revolutionary angle adjustment for pipette. The angle can be adjusted through a wide arc from 15 to 40 degrees. The pipette never leaves your sight, eliminating worries about broken pipettes. Commercially available micropipettes often suffer from imprecise bending angle. The included angle gauge enables you to adjust for deviation to the exact angle degree. Feature 3. Traditional oil hydraulic drive. Narishige has a long history of relationship with our customers for smooth movement of oil hydraulic micro-manipulator. Smooth, precise response of the three-dimensional joystick enables operators to pick up moving objects with confidence. The X-axis knob for precise straight line movement enables fine control for puncturing a fixed target. Only the Narishige oil hydraulic drive can perform both of these operations without switching. Feature 4. Radically simple installation in microscopes. No adjustment is required when attaching the mounting adapter and drive unit. With this, stability is significantly improved. Feature 5. Simple motorless microscope operation. No power supply is required. so the area around the microscope is uncluttered. A single slit tube bundles together the oil hydraulic tube. These are the names and functions of the principal.
というわけで、ちょっとさっき言ったら間違いで、ここはこれエアとは使わなくて、if you use air has some damping effect, so therefore the oily hydraulic system mainly used. Okay? というのがこれですね。で、あとはまあこれはなんか piezoelectric system is used to the smooth insertion. For example, the previous system, if you use some mechanical or electrical movement, it is some damage to the membrane. Looks like this. これピペットで、これインジェクションってこれが some cell is fixed to the end of the pipette ね、pipette で some needle is inserted here で、この piezoelectric stage is when we use a piezoelectric stage, more smooth movement is there, so therefore the insert of the membrane more smoothly っていうのが this system ですよとか言っています。これ more than これ 1990s about というわけで、オプティカルトゥイーザーとかmaybe glass micro needle is also used, and the AFM atomic force microscope is used to by using the cantilever and making some forces applied to the cell, and the surface shape or mechanical property of the single cell can be measured. で、サイトプラズマとビスコシティは inside of it, there are many organs is inside of the plasma, so therefore it is depending on its part or some data, different data is reported. So many methods there I will explain later. And also the viscoelasticity or contraction force is also the micropipette method, and the pulling force is measured, and the AFM is used. Cantilever is some probe is pushed on the cell. で、ここからがsome measurement example で only one single cell is put on the plate. Therefore, firstly it is when it is floating in the liquid, it is a circular shape, sphere shape. But on the gravity condition, it can be deformed. So therefore, some time scale and its the deformation, we can estimate some surface force or some tension about the membrane can be estimated depending on its curve. This curved shape like this or like this or something. Then some gravity is applied. So, or some more the centrifugal force is applied, not only 1g, but also another more larger gravity is applied, and then this deformation can be observed. So therefore, this deformation shows the viscoelasticity inside of this plasma and also the membrane. The other method is using the plain plate, and the pushing force is applied. When some pushing force is applied, the deformation and the force ratio can be measured. So therefore, the inside of the pressure, inside of the cell, the pressure of inside of the cell can be measured. And also, this is another way. The only slight difference between between left side and right side, some pressure force is applied, is made by using this water level difference. So this water level difference makes the slight difference of the pressure, water pressure. So therefore, the one single cell is put on the inside of the hole, and then some pressure force is applied here. This array-shaped cell is moved by pushing of the water. So therefore, by using this pressure gradient as a deformation way is observed, and then this plasma's characteristics and also the membrane characteristics can be measured. This is another method. And this is a magnetic particle method. Some material, it has some magnetic characteristics, so therefore is inserted inside of the one cell, and then at that time some magnetic field is applied. For example, this is from here the zero magnetic force to this step response. Some magnetic field is applied and then released. So some force is applied on this particle, on this material. So therefore, its movement looks like this. When during the force is applied, and the movement looks like this. And then the force is released. The zero force is applied, and it will become going back. So therefore, by using this tendency, while its time goes, the temporary change of time, this mechanical feature, dynamics feature, the viscoelasticity can be measured. Right. This is also the micro-pipette technique. One single cell is sucked by this pipette, and then some force, negative force is applied, so therefore this membrane will deform like this. So this is the time, and the suction force is here, negative suction force is here, and this positions, the time changing, temporary changing of this position is measured like this. In this case, it is go back to the original position, original place, almost original place, then the suction force is released. So some cell's case, or another cell's case, another cell's case. So therefore, the surface force can be applied, can be measured. By using this micropipette method, the vascular endothelium cell is measured. For example, the suction length and the difference in pressure. これは何ですかと言ったら、これはインバスキュラーセルのバスキュラーカナルのこのウォールセル、このウォールセルね。で、なんかプレッシャーフォースっていうか、プレッシャーフォースのプレッシャーグラディエント from this basement, and this is a peripheral force, peripheral method. So P1, P2, the P1 is larger than P2, so therefore some blood is flowing. So when this difference is changed, this is tau. So the high pressure difference is make high fluid, faster fluid. So therefore this membrane cell, this wall surface cell is become harder like this. So therefore this tau is, when tau is changed, this cell's membrane, this cell's mechanical characteristics become harder like this. ね、だからこのプレッシャーフォースのこのプレッシャーフォースのディフェレンスを if it changes pressure force difference, some sharing stress higher shearing stress is applied when this difference forces become larger. Shearing force is applied, more higher shearing force is applied. So therefore the surface membrane, surface cells membrane is become harder. This is observed by using this. When no pressure force, no gradient force is here, the higher gradient force. So therefore the higher cell membrane's characteristics can be observed. So therefore the details observed like this. これはどんなやつですかって言ったら、ちょっとこれを見てみると、これは何ですかと言ったら、これはある some one group is made some measurement system by using the image processing techniques. This is cell. Cell is observed by camera, and the camera is observing this shape of the cell, and then this is a pipette, the suctioning this cell membrane surface, and then the deformation is also observed by automatically by the target cell を決めて、でそこにthis tube is this pipette is mechanically closed, and then the suction force is applied, and then the membrane's shape is measured by using the image processing method. Yes, like this. And then automatically measuring the force, suction force, and this deformation is calculated based on the image processing method. So therefore, automatically some response or something is also measured. So this system is made by this group. This video is introducing about that. ということでした。ということで、これはおしまいで。はい。と、同じように、これは、some miniature indenter というのは、だから、あるセルに、なんかこれをプッシング。で、このカンチレバープッシング and then the deformation of cantilever and例えば some strain gauge method and this force tension can be measured, and then this deformation can be observed by image processing method or something, and then so therefore some cell, the first cell, second cell, third cell, and so on. This cell is used, and then the length of pushing into this indenter, and then the weight load is measured, and then this curve is observed. これはどっかにこれも例えばあってイメージライブラリか。例えばこれですね。これでなんかこれをここがセルでここにプッシュすると。これはサクションしてるパイペットですね。でここにこれをプッシングしてて、でこれ感じればだからなんかストレインゲージメソッドとか something で the force applied force can be measured, and by image processing this deformation can be processed. So therefore this cell's dynamic characteristics can be measured. More pushing. ですね。ここになんかタイム書いてあるんですけど、見えますね。とかやるわけです。です。
experiment is to measure the elastic modulus of living cells using an atomic force microscope. This is achieved by first performing AFM force spectroscopy measurements at various locations on the cell. As a second step, every force distance curve is analyzed to determine the point where the AFM tip initially makes contact with the cell. Next, starting at the point of contact, the first 200 to 300 nanometers of indentation data are fitted.
というように、なんかこういうピペット、カンチレバーをプッシングで、some deformation can be measured ね。とか、これはちょっと違っていて、これはワンシングルセルをこう引っ張る、プリングエクイプメント is developed。で、メカニカルテンションテスト。Mechanical tension test to be applied to this single cell. Maybe if you are the mechanical engineering course student, you have done something about the なんかこのロットをこうチャックしてさ、チャッキングロット to some machine, and then it is a pulling test that has been done maybe, and it is deformed. なんか like this とか、like this とか言って、この deformation of the some lot test piece you have observed, maybe the pulling it, and then it is look like this, and the breakout. The release. Maybe you have done in the mechanical engineering course student some basic experiment, maybe, and then it is similarly this. The one single cell is chucked by the suction by pipette, and then on both sides it is the pulled. This is one part is fixed, the other part is micro-manipulator is there, and this using this micro-manipulator it is pushed. And then some applied force is measured by load cell, and then this is the one result. This is the length of the length of the between one cell, and then the applied force is shown here. So the F1, F2, F6 means some first cell, second cell, third cell, the 6 times operation has been done. And this is a similar result has been observed like this. なんでこうなってんだろう。あんまりいいや。ということで、by using this various materials, various cells, mechanical dynamic characteristics can be observed. 例えばこれはレッドブラッドセル、これはホワイトブラッドセル、これは the エンドセリアルセルとか about for example this is the fibroblast cell とか some nerve cell これ in the case of the human being and this is octopus じゃなくてなんだっけモスキートじゃなくてなんだっけ I don't remember about that but some of the fiber cell or nerve cell is measured so therefore the size of the cell and the viscoelasticity of each cell can be observed, can be measured. So this is the basics of some the modeling and because for example なんか例えばハートシミュレーターってハートねHeart simulation is presently done in many countries, in many organizations. Yes, なんか chambers, 4 chambers movement, and also this is some muscle model is here, and then it is some single cell is here, and by using this single cell's characteristics, this shape of this organ's shape is modeled, and then the total movement is also estimated by making some stimulus to each stimulus is also from generated from here and transferred like this from here to the firstly about this, secondly about this. So therefore this transparency processes is simulated by using some supercomputer and so on. To realize this, the single cells mechanical characteristic is necessary to model of the simulated heart. So therefore, this kind of the basic measurement of single cells mechanical characteristics is important. Okay. で、これはセカンドパートおしまいね。残りはサードパートなんだけど、サードパートは remaining 10 minutes. So this is one part is birth. Birth is all of us is firstly from the egg cell and stem cell. And then the fertilized egg is generated. This is a single cell, so therefore the some bird cell is the most largest in the world. And then the copying the genetic DNA, and then it is separated into the many kinds of various cells, and then the forming this human body. これいいですね。おしまい。で、あとバースはこれで、not only the fertilization, but usually we are doing the division and regeneration. So the division and the regeneration is look like this. For example, the liver or kidney, it makes the usually once per 1 or 2 years. The next by division, the next new cell is reproduced. The copy of the cell is reproduced. But the number of copying is limited because of the telomere. This is a very important discovery in the 1960s. So after some number of division, this cell cannot be divided into new cell and cannot reproduce new cell because of the telomere. And the upper yes, we are from the one single cell, fertilized cell, and then it is divided into some cells, and this is a source cell, and also it is also divided into more specific cell is divided. So therefore, at this stage cell is called the stem cell. Stem cell is called at this level, and from this stem cell, the several cell is divided into some specific cells. So therefore, it is also another way to the generation. No time to do. So the cell division method is the meiosis. Cell division is divided into two types: meiosis and somatic division. Meiosis is only for the birth, and the somatic cell is a usual divided reproducing. Okay, usually reproducing. And this somatic division, the plant cells method and the animal cells methods are a little bit different. It shows. で、テロメアの話だけど、when copying the DNA, the end part is called telomere, and it looks like this. なんだ？これが DNA テンプレートで、primer RNA is copying of this template, copying template, and then this primer RNA part is separated. So therefore, the copied DNA is a little bit shorter than the template DNA. And then, so therefore, this part is called the telomere. Yes, telomere part and the template DNA part. Primer primer RNA is attached, and the primer RNA is working as copying this RNA DNA, but some end part is not copied. So therefore, the some telomere part is not copied. So the original telomere's length is become shorter and shorter and shorter, and the telomere part is not here. Some after some generations, telomere is disappear. So therefore, it cannot be copied again. So it explained some videos in after telomere.
Inside a human cell is the nucleus. Inside the nucleus are 23 pairs of chromosomes. These are long threads of DNA carrying the genetic information. Right at the ends of the chromosomes are special stretches of DNA called telomeres. They are known to play a crucial role protecting the ends of DNA.
So we kind of think of this like the tip at the end of the shoelace, because if you don't have that tip, then the end of your shoelace frays away very quickly. You know, your shoelace won't work properly if it doesn't have a tip. And it's like the end of a chromosome, the end of a DNA. If it doesn't have an intact tip on it, the telomere, it too will fray away.
When a cell is replicating, it can't copy its DNA all the way to the end, and so telomeres shorten with each replication. If telomeres get critically short, the cell can malfunction and die.
If you don't have caps on the end of a chromosome, then the ends become very sticky. It's almost like the shoelace ends become tied together, and this messes up the genetic material. This can have disastrous consequences for cells, a little bit like if your ends of your shoelaces are tied together, you're going to trip up and fall.
これ面白いね。It is looks like the shoe shrinks. はい。で、OK ね。で、finally, the death of the cell. Death of the cell ね。Death of the cell is two types. Also, apoptosis and necrosis. Apoptosis is a planned death, and necrosis is a complete death. Necrosis と necrosis のバーサスっていうやつはちょっとどれがいいかな。これかよくわかんないけど。これはネクローシスというのはなんかウイルスとかバクテリアとかでメンブレンがディストロイとかして or the nucleus is become larger and inside of the some organelles is become larger and larger and the size of the membrane is break out and then this cell is dead. で、アポトーシスは何ですかって言ったら、ミトコンドリアがインヒビトリーシグナル出してで、中のものをなんか壊してしまう。Destroy the inside of the membrane とか inside of the cell で DNA もブレイクアウトでニュクレウスも disappear で this is a なんか not cell っていうようになりますよとかいうのがアポトーシスですよ。ね、アプローチとはこうです。ネクローシスは some other external なんか stimuli is make the cell dead and the apoptosis is このなんか DNA is destroyed and the separated in the small size. So the necrosis is very important because this is made by some microcardiac infection, the liver damages, or radiation is make the cell deaths. And also the muscular dystrophy. Muscular dystrophy is the one part of the necrosis. And also the frozen of the end of the peripheral, the fingertip or the toe tip is become dead. Some of the cell is dead. Frostbite is one of the necrosis. And also bed sore. When some elderly people is lying on the bed forever for many hours, his hip side or back side is become the bed sore because it is not some blood is new blood is not applied to these cells, so therefore the bed sore is happening of some elderly person's back on the hip side. The apoptosis. Apoptosis is very important. Maybe you may find some of the case. The many babies inside of the mother's body is look one attached finger, hand has there. But between the finger, this cell is destroyed, dead. And then we can move individual fingers. It is similarly, this is same. This is the duck case and this is a chicken case. Duck and chicken case. Chicken case is between fingers. It will be destroyed. This cell is destroyed. But the duck's case, this is makes a fin made. So therefore, it's not destroyed. Okay. So this is a webbing, and the fin is here. So the cock case and the duck case is a little bit different, even though it is the same bird. This is programmed somewhere. The final information about the ISIPS 2017. This graduate school is annually we will have some symposium with some accompanying universities abroad. So therefore, this 14th, 15th November, we will have a symposium, two-day symposium. Many students in the laboratory in IPS will present the oral presentation or poster demonstration sessions. So therefore, if you have some time, if you have some room, you should watch, you should attend some interesting sessions or some poster sessions. これこういう時間にやってますんで、the detailed program you can find this ISIPS website. Keynote speaker Professor Baba and invited talk Professor from Shanghai Jiaotong University will present something about the wireless something. Okay. So therefore, if you attend there and you will bring some report, I will give some additional point to the usual scores. Okay. Yes, this is one information.